Let's get started. So welcome back, everyone. So it's a really nice day outside and like a great day to learn about spectral clustering. So um, that's what we'll do today. So this will be kind of the third in the series on clustering, and this lecture is going to also give a preview into some ideas we'll explore more in the second half of the class in dimensionality reduction and in working with graphs. So we'll get to do that a little bit. Let me just start by reviewing the schedule where we are. So the clustering homework is due on Wednesday. Did any of you have any questions on the clustering homework? This is mostly going fine. There have been some questions on Canvas. If you haven't seen those, hopefully those will help clear up some possible interpretation issues about stuff. But so seems to be going well. Okay. Again, this one will have a few things like which variant did the best job? How many clusters do you think the right number of, the number of clusters there should be that are intentionally open-ended without kind of one, you run this algorithm, it outputs a number and you write down that number, right? It's meant for you to kind of try and reason about it and kind of think about these different options you have before you. As is, again, common in data mining, for a lot of the general cluster problems, there are several, if not dozens or hundreds of options of algorithms to run. And so there's not always a clear winner or way to kind of judge which one is necessarily the best. So you need to use your judgment. Yeah.
Let's clarify. Part C on we're doing this noise algorithm stuff over C2 context, correct?
Yes. Everything about question 2 should be on data set C2. Yeah, that's correct. Great. So, okay. And let's see. There have been, looks like the website's back up and working again. Hopefully, I've been told over the summer I need to host my website someplace different, but hopefully it holds up through the end of the year. Why it's so hard. All right, so then after today, we'll have a short section on streaming algorithms and counting frequencies of things. This will be on related to at least the sort of things we'll talk about here related to these kind of representing high dimensional discrete distributions of objects. Be thinking about if you're sitting on like a router, what information can you mine from all the packets running through the router? Those sorts of questions. And then the midterm tests be next week on Wednesday. Okay, that will be in class. You will get to bring in one sheet of paper, front and back. You can put anything you want on it. Okay. Hopefully you don't find an advanced copy of the test and put that on there with the answers, but anything, anything you want, you can put on there. The idea is to help you study by transcribing what you decide are the most important things onto a sheet of paper. You will not be allowed computers or calculators or anything like that. You should not need calculators for anything. There's a practice example. Let's see, this is one of these. Okay, this is an old practice exam from a number of years ago. I've emphasized slightly different things, but I think it's an okay representation of what the test will be like. The midterm may be a little bit longer than this. I think it might have like 4 questions instead of 3, but I think if you're following along and can basically answer these sorts of questions, you shouldn't, I don't suspect you'll have a problem finishing in class, but you'll get the class times the 80 minutes of class to work on this. All right, it will be in person in class. Okay, yeah.
So when you mentioned the years, it's mostly because of time.
Yeah, I'll ask you things that if you've been following along in class, then the main takeaways from, the questions, each question should ask you something about a main takeaway from some of the lectures. It's not going to ask you, okay, what color shirt was I wearing on Monday the 23rd or something like that. It should be one of the main points of these lectures. Okay, yeah. So, and I try and hopefully you'll get to work through some algorithms, evaluate some things, but it should not be mostly like memorization either. It should be, if you know the big concepts, you should be able to do it, but there are some simple algorithms that you should be able to work out pretty simply by hand, or calculations by hand. Those are the sort of things you should be able to do on the midterm. Okay. All right, and so you get questions about stuff, you can ask me, but I think if the practice test seems reasonable and you've been following along, you should be okay. All right. Great, and then we have spring break. Yeah, sounds good. All right. So let's talk about spectral clustering. So we've talked about clustering. Okay, and so far we've said the input is going to be a data set X, X1, X2, ... and some distance. Okay, we're going to change it up a little bit today, and instead the input, instead of the distance, it's either going to be a graph, which I'll explain, or a similarity function instead of a distance function. So if you have a distance function, you can often convert it into a similarity function, and we've talked about that transformation back and forth, but sometimes it's more natural to talk about a similarity function. Okay, and this will convert more pretty directly into the input representation we'll have for spectral clustering. We had to just review some context. We talked about 3 types of clusterings. The first was hierarchical agglomerative. And this also included the density based clustering. And so this was very much bottom up. It was, and it basically worked, find 2 close sets and then merge these sets into kind of a join them together into a cluster, and then recursively apply this. Okay, the second set we talked about were the assignment based. Okay, and the goal here was to find these centers C1 up to CK, and then this implicitly, once I'd found these centers C1, C2, C3, it defined this Voronoi diagram, and then implicitly it mapped any of the data points based on this Voronoi cell it was on, based on which of the centers was the nearest neighbor, onto that center, right? So we assigned each of the data points in X, the purple points, onto one of the centers, and this was implicitly defined by the distance function. Also gave us these nice representatives. right? The centers were representatives of each of the clusters, and maybe and there are a bunch of formulations. K-means is probably the most famous, and K-center is another one I like. Okay, the third type, which we'll talk about today, and kind of within these three is probably 98% of all variants of clustering. There's huge variety of these sorts of clusterings, and there are thousands of research papers saying, haha, my new clustering is the best. But kind of most fit in these three categories. So the last type will be spectral clustering. Okay, and this will differ from these other ones for a couple ways. One is going to be top, down. All right, so the hierarchical is bottom up. I kind of merge things, or even the DB scan we talked about, density based. You're kind of merging things which are nearby to each other, and that building these groups. This will be top down, which means that I will have a bunch of data points. Okay, and so what I'm going to try and do is I'm going to try and find a good way to split. Okay, and then recursively within these two clusters, I might find another way to split these, right? And you recursively down. So again, I'm going to build this hierarchy, but it'll be a top-down algorithm where I'll be splitting instead of merging from the bottom up. Okay. The other ways is as I mentioned at the top of the slide, is that the input will often be a graph or a similarity instead of a distance. Okay, and we'll talk about that modeling. And then, and we'll have a whole section, the last section in the semester, we'll be talking about graphs. So this is a preview. We will also get a preview of, dimensionality reduction. Okay, so this spectral algorithm is often used kind of implicitly or explicitly doing dimensionality reduction. Sometimes it's used where they'll do the dimensionality reduction part of this, and then they'll run k-means algorithm formulation on top of the dimensionality reduction. That's a kind of a common pipeline that is sometimes used. Okay, so this is kind of where spectral clustering fits into this kind of space. And let's see. So let's talk about graphs. So the input to the spectral clustering algorithm I mentioned will be a graph, and sure, if you've come up through the kind of school of computing, then you've probably seen graph representations of data before. We're going to think of in this representation that there are a couple ways of representing graph. The first one will be kind of a vertex edge set style, and so we'll think of the vertices as like the color. The vertices will be like the data points. Okay, so think of the vertices A, B, C, D, E, F, G are going to be the data points in the graph. So these could be much larger. So think of an input graph, what could be like people, and it's a social network graph or a web graph. These are things we'll talk about later in the semester. So then in the social network, the vertices are people, right? Or users on the social network. They might not actually be people. It could be bots or companies. Or in the web graph, they could be web pages, and the edges are like links between them. Okay, and so we'll be measuring the similarity or the distance using the vertices, using the edges. We'll somehow need to use the edges to determine how close things are. Okay, and kind of it's worth pointing out that in this representation, we'll think of these vertices as like a set, which was similar to the data points before. There wasn't ordering, but also with the edges. In particular, when I look at a single edge, EG here, which represents this edge between vertices E and G, there's there's not an order. There's a version of graph that we'll talk about later on in the semester where you'll have these directed edges. We're not going to talk about directed edges today. And so I've seen some studies from people I trust that basically comes to the conclusion that if you want to do sort of clustering where your input graph has directed edges or something like that, pretty much the right thing to do is to treat them as undirected edges. Okay, it gives. So we're just going to pretend all edges are undirected. There's not a direction between E and G today. Okay. All right. Another way of thinking about a graph, a different way of representing it, will be as a matrix. Okay, and we'll talk about this representation. All right. So this representation kind of, you can think of it as the table. I've written as the table on the left, and then you can write this as just a matrix, but the table has labels on the rows and the columns. All right, so that means that if I have kind of point A here, then I'm going to have a 1 in the locations where it has an edge. These are the edges to other vertices B, D, and C, and a 0 if I do not have an edge. Okay, and this is a symmetric matrix because the edges are not directed, right? So you'll see that in the same locations on the row for A, I also have an edge, because that would also mean an edge from B back to A. Those edges, the direction doesn't matter. Okay, so this is a convenient thing about if I have an undirected graph and I represent it as a matrix, then my matrix is going to be symmetric. All right. So what are advantages of using this vertex edge style of representation of the graph versus the matrix style, or vice versa? What do you think? Yep. If the graph is really dense, you like the matrix style better. Why is that?
Like all the edges.
Yeah, okay. So what was brought up is if you have a dense graph versus a sparse graph, right? A sparse graph there's not a fixed definition of it, a precise boundary, but it means that you have sparse means you don't have a lot of edges, which means that the matrix representation is going to be mostly zeros. Look at this whole block here in the corner, right? This block down here. This is, there's lots of zeros. So this is pretty sparse because it's mostly zeros. And there are some very sparse matrices where they are kind of 99 or even kind of, even more than that percent of the entries are zeros. If they're dense, then you have basically most of the entries filled, maybe half the entries filled, right? Or even if it's 10% of the entries filled, this might be fairly dense. And then this gives kind of a more compact way of thinking about it. Whereas if it's sparse, well, then I've stored space for a lot of these zeros, which it didn't have any information in it, basically. I'm better, more compactly representing it as the vertex edge set, but that may not give me as better data structures or algorithms, we'll see, that I can apply on them as easily if I have the matrix representation. Do you have anything to add to that? Yeah, so if you wanted to quickly look up an entry, I wanted to say what is, or let's look over here. I wanted to say F and D, and I stored all of this, could fit everything in memory, right? Then I could quickly in RAM, in random access memory, I can look up this up in constant time to see what's here. Whereas by the set representation, I want to know if D and F is going to be in the set or not. To do a query of a set, I could use maybe a hash table data structure and look it up, but it's not quite as clean. If this all fits in memory, then this is much easier to work with, right? So if memory and space is not an issue, then the matrix has a lot of nice features to it. If memory and space becomes an issue, I may want to use the vertex edge set representation. It's more compact. It only stores the information I need. Okay. There's something kind of in between, which would be a sparse representation of like a matrix. The sparse representation of a matrix, the interface as a user of a data structure is basically the same. I can do lookups and stuff, and I can pretend it's a dense matrix, but it's stored internally different. It'll somehow think of like storing in every row the gap in between the ones. It'll just store the location of the ones. So kind of like that in this set, but it stores them kind of in a nice order, and I just have to store the distance between them. Now, lookup is not quite as fast as if I had here. Maybe I internally have a hash table or a binary tree on top of these, but the data structures have been pretty well optimized. They work pretty good. So you can do sparse representation of matrices. In fact, there are algorithms to kind of do matrix multiply and all sorts of stuff with the sparse representations. They're not always implemented perfectly. I don't know. About 10 years ago in Python, we had trouble with some of their sparse matrix implementations. I haven't checked more recently, but they're a little trickier to get everything right. But in MATLAB, for instance, stuff works great. Okay, so these two representations. Okay, so I guess the next question is, what do we think about clustering on this graph? What would a clustering on what do we do to do clustering on a graph? Okay, I'm going to now think of, I'm going to start without going to the matrix representation. We'll come back to that. We'll think of the kind of the set representation with the vertices and edges. And I somehow want to cluster the vertex set V, right? Okay, so how would I cluster the vertex set V? And while you're thinking about this and thinking about raising your hand to tell me the answer, remember, we're going to do a top-down clustering. So we're going to take the graph and we're going to split it in two pieces, which is all the vertices split in two pieces. Then we're going to apply this recursively. Okay, so to do clustering, I somehow need to partition the vertices into two sets. All right, and I'm going to do a two clustering of the vertices in the graph. So that's the core problem I have now. So what would be a good two clustering? Yeah.
Just pictorially speaking, cluster, some sort of thing separating in between that edge. C. Not sure how you would calculate it, but something akin to like there's only a single edge connecting group or a very small amount of edges connecting group. That's where you want to do the division between the groups, the clusters. So
I somehow want to find, I want to find a place where I can cut the graph. I want to somehow cut the graph, and I can think of it like a dividing line, but really I should be circling a piece I'm cutting out of it, and then everything else is in the set. So I want to find a I want to do a split of V into two sets S and T. We'll call this set S, and then T will be V set minus S, right? So T will be everything left over. So all this stuff over here is T. Okay, I somehow want to cut the graph in this way. Okay, and how do we determine, right? How do we determine what's a good cut? Okay, we're going to use the edges to measure the split, right? How good is the split? We're somehow going to use the edges, okay? And this cut, this way of splitting was kind of nice because the way I've circled S, I've put all the vertices inside S and inside that purple kind of loop, and I've only crossed over one edge. Okay, this seems like a good thing. Okay, so so often we could think of the first approach, which think of the cost of a cut between S and T. It's going to be the number of edges in E, which is the edge set, such that so for an edge V1, V2, I have V1 is in S and V2 is in T, right? So it's the number of edges that cross over the cut. C, this would be like V1 and this would be like V2. V1 is in S, V2E is in T, and that edge between C and E, between V1 and V2 is part of the cut. The cut is the number of edges which have crossed. Okay? So is this a good thing? This is a good measure of how to cluster? Number of edges I've crossed here is 1. It's pretty small, so that seems pretty good. Okay, what if instead I said this was my S prime? Okay, so then I can define T prime as everything else. Let me put my T over here. Okay, so now T prime is everything outside of S. And so I also have I also have that the cut of S prime T prime is equal to the cut of S T, which they're both equal to 1. Okay, so both that purple cut into S and T and the green cut into S prime and T prime, they both go over exactly one edge. All right, so okay, do you guys think, okay, which one do you think is better? Who thinks the S prime T prime cut is better? And who thinks, okay, one hand, okay, good. And who thinks the ST cut is better, the purple? Okay, all right. So why do you think the ST prime cut, the ST cut, the purple one is better? What? Raise their hand. Yeah.
There's maybe there's an even number of vertices within.
Yeah, so it's the purple one is more balanced. Yeah.
For S and T, it preserves regions of density. Like the density of edges, you're cutting away that one edge, you still have 2 clusters that are added.
Yeah, so the ST cut, the purple one, preserves regions of density, right? It's the density within the S part as well as the T part is denser than it was if I took the whole graph, right? And I'm not quite seeing that with the green cut here, right? So that one also seems better. Yeah, these are both great like intuitions for how to do this. Okay, and so when people design spectral clustering algorithms, they usually don't just use the cut size, which you would optimize if you were doing kind of You could optimize cut with a min cut flow through the graph if you take an algorithms class, but this is not what they often do, right? Because you get these little tails and you cut these little vertices off on the edge, and that's not really subdividing your graph. It's not preserving these regions of density. Okay, so what the common way people measure how good a split is something called the normalized cut score. Okay, and so this somehow tries to enforce that the split is going to be balanced, and then I'm preserving some sort of density on both sides. Now, there are some ways of thinking about this where I want to explicitly measure the density. This turns out to be harder to do. And there are some algorithms that will be much more combinatorial, and you have much more bigger combinatorial search to try and optimize that. Normalized cut will have a cleaner method using the matrix kind of representation, which is what we will build up to. Okay, so how do I define normalized cut? Okay, I need to look at what I call the volume of a subset, and this is kind of like what the density is, and this will be the number of edges with at least one end point in so in S. Okay, you could think of, if I have, again, I think of the volume of the subset S up here, maybe I just want the edges that are in between, but the common notion of volume is they just have one endpoint in the graph, so I could have an edge spans the cut, that's counted as part of the volume. Okay, this allows me so that if the graph is connected and every vertex has at least one edge, if I divide by the volume, I'm never dividing by zero. Okay, so it's convenient for that way. Okay, and so sorry, I'm losing my voice. Okay, so on the previous example, remember in the volume of S before, which was the purple cut, this should have been 6. Let's see, I have 1, 2, 3, 4, 5 entirely inside, and the one I cut going across. And of T should be 1, 2, 3, 4, 5, and the volume of T is going to be equal to 5. Where if I look at the volume of S prime, this was going to be 1. Remember, S was the smaller piece, and volume of T prime, I think it was going to be 10. Okay, that there are total of 10 edges in this graph, and they were all in the volume of T prime. Okay, so now we can define the normalized cut of ST, and it's going to be the cut of ST divided by the volume of S. Okay, and this is not symmetric, so I want the cut to be small and the volume of the subset I found to be large, right? So I overall want this to be, the normalized cut to be small, right? So I want the volume to be small, the volume to be large, so I have a lot of edges involved in that side, but this is, I can still, if I chose T prime as the cut, then this would still be big, right? So this, I need to make this symmetric to both sides, and to do that, they do plus cut of ST divided by the volume of T. Okay, so this is how they define the normalized cut. We can now compute this. Okay, the normalized cut for ST is going to be, the cut size is 1, and the volume of S is going to be 6 plus 1 over 5. And this is equal to about 0.367. Where if I look at the normalized cut of S prime, T prime, I'm going to have 1 over 1 plus 1 over 10. Okay, the 1 over 10 is good. This is a very small term, but the 1 over s is going to dominate this, which is 1, and this is equal to 1.1. Okay, so now the normalized cut of the balanced ST is much smaller than it was of S prime T prime. Okay, so this is giving me kind of a thing that is accomplishing kind of what we decided we wanted as a class. We voted. So sorry if you voted for the other cut, but if you liked the ST cut, then the normalized cut does a good job of optimizing this. Yeah.
So our goal then is to minimize.
Yes. So we then want to try and find the cut that minimizes the split that, or the subset S that minimizes this normalized cut. Right. Okay. So the goal is to find S subset V to minimize N cut of S V minus S, and then recurse. Okay, and this is kind of our clustering. Again, this is defined procedurally so far. Okay, it's defined procedurally. I want to minimize normalized cut and then recursively do this until I'm satisfied. Okay. Okay, great. Okay, so how do we minimize a normalized cut? So, I mean, if you look at this example, all right, there's not too many things to check, but if this was a much larger graph where the edge structure is much more complicated, that's seems like a harder thing to check, right? How many different, if I have n vertices, how many different subsets do I have that I would need to possibly check? How do you count the number of subsets that could be S? Should be from, if you took CS 2100, right? Should be a question from there. How many subsets of a from a set of size n? I can mark something 1 if it's in the set and 0 if it's not in the set. So how many ways can I do that? 2 to the power n. Yeah, there are 2 to the power n different subsets. I don't want to check the normalized cut score on all of those. That seems time consuming. Okay, so so to minimize this, there's not, it's kind of like with the k-means clustering formulation. We had Lloyd's algorithm, which kind of iteratively was improving this. But if I wanted to check all of them, there might be a lot of different subsets I would need to check. And that's why those clustering algorithms, I didn't tell you how to exactly optimize those formulations. I told you ways that kind of did their best effort. This is a hard combinatorial problem. And some versions of these, you can set them up to be kind of, some versions are to be NP hard, in fact. Okay. Now, can I minimize the normalized cut? Well, I'm going to describe an algorithm that goes through the matrix representation to, again, it's not going to guarantee to be able to minimize the normalized cut, but it's going to kind of statistically do pretty well. Okay, so I won't be able to say super strong guarantees, but it will eventually be trying to optimize the right thing, and tends to work well in practice. And again, these are kind of modeling choices, and so you shouldn't treat them too seriously sometimes. Okay. Okay, so what we're going to do is we're going to build something called the Laplacian matrix of the graph representation. Okay, and it has got 2 ingredients in it. Okay, the adjacency matrix, which we already looked at, right? This has a, if there is an edge between kind of A and B. If there is an edge here, then I put a 1 in this entry, right? We talked about the adjacency matrix representation. This captures everything of all the information is in here of the kind of undirected graph, okay? And then there's also the degree matrix. The degree matrix tells me something about, if I look at a node, let's look at node E here, which is this node. Okay, this is on the diagonal. So I only have entries here on the diagonal of the matrix. So it's that the row and column correspond with E, and it has a 3 in it. That's because it's got 3 edges coming out of E. Okay, the degree of E is going to be 3. Okay, and so that's what's in the degree matrix. The adjacency matrix might be n squared quadratic size, as many edges as I might have. The degree matrix, I know the off diagonals are all 0, so it's only linear size. I just, for each vertex, I store how many edges it has. Okay, so also pretty easy representation. And then the unnormalized version of the Laplace, of the Laplacian matrix of the graph is just going to be D minus A. Okay, we'll call this L0. Okay, this is again a matrix D minus A. And okay, that's what the matrix looks like. One way of thinking about the unnormalized version is if I look at a node A and I look at, it has a degree of 3 that's represented here because it's D minus something. If I have no self loops, which I haven't, let's not worry about self loops in this part of the class, a node to itself, then all the diagonal entries were 0 in the adjacency. So I can read off the diagonal on there, and everything in the adjacency is now is negated. And I have a negative number, and I can think of this as the information flowing out of here. So I have a degree 3, and I can output it in the column, right? I have one part of the degree going to B, one part to C, and one part to D. Okay, it's kind of a measuring something like a flow going through the graph and just have this balanced flow sort of way of thinking about it. Okay. Okay, and then once I have this matrix representation, this unnormalized Laplacian will be able to somehow capture the cut information in here. Okay, and the question is, how does this capture the cut information? Well, I need to apply some linear algebra. I'm going to do an eigen decomposition on this Laplacian matrix. Okay, so what does this look like? I'm going to do L0. I'm going to represent, if you remember the eigen decomposition on n by n matrix U, a diagonal matrix lambda, and another version of matrix U again. It's transpose. It's going to be an orthogonal matrix or orthonormal. So I think I don't even need the transpose because it's its own transpose. Okay, and this is going to store the eigen vectors in U and the eigenvalues, because this one is going to be so diagonal. These are going to be the eigenvalues. Okay, and let's calculate them here. Okay, I went and calculated all this. So I did in V instead. So these are going to be the eigenvalues. So for instance, this one will be important. This will be the second eigenvalue, V2. And these will be the, I wrote the wrong thing there. These are the eigenvectors, I'm sorry. these are the eigenvectors, and the values on top are the eigenvalues. So this would be lambda 2. I made lambda 2 in bold there. It's important. Okay, this is somehow going to give us information about how to determine a good cut on the graph. Okay, and so a couple things to look at here, and I'm not going to derive all this. I'll kind of just tell you how to look at this. The first eigenvector here, the first column, this seems not very helpful somehow. The eigenvalue indeed will always be 0, right? So this one, this is always 0. So that's not going to be too helpful, okay? And these guys will always be the same. And they're always 1 over square root of n. Okay, so this is, again, not too helpful. It's going to be basically true for any graph that's so connected. I'm going to get this. So the first one is not going to tell me much. I've sorted the eigenvalues in an increasing order. The second one, this one is going to be very useful. This is called the Fiedler vector. Okay, and this tells me how best to map to one dimension. Okay, it's basically telling me how best to map the vertices into one dimension here. And this is kind of a magical property that's going on. What I'm going to do is I can think about drawing a line here between basically -1 and +1. And then I'm going to be able to write all the vertices onto this line using the Fiedler vector. Where did stuff go? Looks like I somehow jumped ahead here. Okay. How did that happen? Okay, so I'm going to map these data into one line here. -1, +1. And I'm going to draw each of these vertices. I'm going to draw at right here at -0.36. Okay, that is actually, and is precisely the first value here. I sorted them. The rows are A, B, C, D, E, F, G, H up to H. Those are the ordering here. So A is -0.36. Okay, so this was the value for A. The value for B was a little bit further 0.46. This was B. C is going to be here. C -0.2. And then D is going to happen to sit in the same location as A. Then I'm going to put, let's see, E is next. E's got a 0.17. And this is positive 0.17. F is going to be 0.36. This is F. G is 0.31. And then H, it's probably not that far over, but it's going to be H out here. Okay, so I've kind of used these values to sort them onto a one-dimensional line here. And so I've kind of turned the graph into a one-dimensional representation. Okay, and so then I can find a cut, and there are two common ways of finding the cut. The first one is just to look at this value 0 and just cut at the value 0. Okay, and what this is doing is I'm basically saying this are the positive values, these are the negative values according to the second eigenvector, the Fiedler vector. Okay, so I've mapped them into this one-dimensional space. I can write their values up there, which are the values I see here, and then I can just find this cut. Okay, this is what this is trying to do, is trying to take the graph and do something like preserve the normalized cut, or the group things together that are similar in terms of the graph. And it has to do with, if I were to take a kind of a random walk, where would I be in some one-dimensional space? This is kind of representing the best one-dimensional representation of this. And so I can just split on 0, but sometimes that's not the best thing to do. I can also take this one-dimensional representation, and then I can also, sometimes this representation will look like this, where I have +1 and -1 here with 0, and my location of my data might look like this, where I have a kind of a fairly natural cut happening here, but there could be one of the items, maybe this item A, is just across the 0 boundary, and it groups more naturally with all the things which are positive. Okay, so sometimes I want to find a kind of an ST cut like this, where I want to keep this one-dimensional ordering, but I want to consider all the cuts along this ordering. Okay, this is not much harder to do. Once I have them placed in the one-dimensional ordering, I can sort them, and I can scan and consider all the cuts and maintain the score of the normalized cut as I'm scanning from left to right. Okay, and this is not much harder, and sometimes this gives me a better representation of the normalized cut. Okay, so this would be, it doesn't add a lot of time complexity, but allows you to search a larger space of the possible cuts. All right, so this is the main idea. Yeah. Yeah, they kind of do. Yeah, I was going to talk about this. Yeah, so let me draw this picture here and talk about it in this case. We can kind of see what's happening here. Instead of just taking the first eigenvector, or the second eigenvector, just v2, I've plotted that, but I've taken the third eigenvector, which is the second non-trivial one, and I plotted that on the y-axis. And now I have a two-dimensional representation of the points. Okay? And so sometimes this is a useful thing to do. One nice thing about this is that sometimes I want to be a little bit more aggressive in my splitting, and the most time-consuming step here is actually computing the eigendecomposition of the matrix. And so once I've done that, well, I don't just want the first eigenvector. Let me get the second one too, and now I can do a better split. Again, I mentioned at the very beginning of the lecture, one approach could be to run k-means, a k-means algorithm on top of this embedding in 2 dimensions. Or what is often done is you would say, well, I'm going to divide this up into these quadrants, these 4 quadrants, where these are the things where the first coordinate is negative and the second coordinate is plus, right? So if I do that, that's first one is negative, second one is positive, right? So I get B, A, and D. Then I could say these are this set. If I look at the first coordinate is positive, the second is negative, then I'm going to get these 3 here, right? And I can automatically get this one. The first one is the first one is, I did one of these wrong, huh? Let's undo this. Okay, so let's see, nope, did it again. Okay, the first one is negative, second one is positive, which are these three. I can do that they're positive, then negative. And I can do negative, negative, I get C. And I can do positive, positive, get H. I can split it into 4 quadrants and do a 4-way split at the top level instead of a 2-way split. Okay, and then I can maybe recursively keep going down if I want to, or maybe this is a good place to stop clustering. Okay, so if I use the second coordinates, then I get a 2-dimensional representation. And this is in some sense, under some measure, I'm not going to describe in the lecture today. This is the best 2-dimensional representation. Okay, so this is kind of why I might want to use these other eigenvectors as well. I want to. One thing I think is worth pointing out here, if we look at A and D, right, these are kind of A and D, these have the exact same values here. So the graph puts them in the exact same location. So why would this Laplacian, the eigenvectors, do this? Why is it? I mean, maybe it was a coincidence that the first coordinate was the same, but the first and the second coordinate are the same. And in fact, if you look here, A and D, right? They have the same coordinates up until this last one, and then only the sign is different. Why is this happening? Is this a coincidence? Yep. Yeah, so in terms of the graph perspective, all they know is what their edges width and then what their neighbors in the graph, where their edges go. And from that perspective, from the graph's perspective, there is no difference between A and D. They both have the exact same set of neighbors, each other, B and C, right? And then from there, B has no neighbors and C only has neighbors with E, but that's the same, right? The graph cannot see any difference between them. So the spectral representation cannot see any difference either. And then finally it has, well, there's one more eigenvector I need, so might as well flip a coin, get one a positive, one a negative sign. And so each of these is kind of telling me some axis of variation in the graph. And the last one is basically arbitrary, the sign of these last two vectors, right? So these other things are kind of meaning something. They're capturing less and less information about the graph. Kind of the amount of information you should be thinking that they're capturing is something like 1 over the eigenvalue. So the smaller the eigenvalue, the more information they're capturing. And this last one is capturing somehow the least information. There are 3 nodes. Yeah, it will. Yeah. So it's going to have to take up 2. It's going to resolve more and more information as it gets further down the eigenvector. So the last 2 columns will have to somehow decide those, and it will probably be it'll be numerically unstable what it actually does. It could somehow be zeros in everywhere except those last 3 nodes, and somehow between those 2 columns, it could be some combination of splitting them so that the norm is balanced appropriately.
I misheard. Did you say that the smaller the eigenvector for a given vertex, the more information?
The smaller the eigenvalue,
Smaller
the value, which is the number on the top here. Okay, the vectors, all the vectors are of L2 length 1. So if I squared all the entries and added them up, they would add up to 1. Negative values would turn positive, right? So if I square 1 over square root 2, I get 1/2. I do it again, 1/2 adds up to 1. right? But that's true for all these other ones. Even a 0.64, well, if I square it, it becomes a smaller number. And if I add these all up, they'll add up to 1. So there's no scale information in the eigenvectors. All the scale information is in the eigenvalues. Okay, well, yeah.
So our original matrix was A by A. Once you can see one in the last. There's little.
Yeah. I'm not totally sure. Let me see if I made a mistake on the slide. Yeah. I'm thinking that's a good question. I'm not sure if I made a mistake on the slide or it actually has 7, but usually only the first few, especially the first one, starting at the second one, is what you actually use. So it's possible I forgot something, but I feel like there's a reason there are only 7, but I don't totally know the answer right now. So that's a good question. I will get back to you Wednesday or on campus. Great. Okay, so I've started with the unnormalized Laplacian, and I'm gonna, and I want to move on and tell you that this is not quite the right way to do it. This is called the unnormalized Laplacian. What you actually want to use is the Laplacian, which is a little bit more complicated. So I started with the Laplacian. There were kind of 2 papers that kind of started people thinking about spectral clustering, and one worked with the unnormalized Laplacian, one with the Laplacian. Turns out the Laplacian, which we'll talk about in a second, will correspond with the normalized cut more directly. This is optimizing something slightly different. Okay. But before I do that, I want to talk about an affinity matrix. Okay. And so so far we've talked about this matrix A, which is this adjacency matrix, which was Aij equals 1 if Eij is in the edge set and 0 so otherwise. But this 0, 1 notion, I think, can sometimes be fairly arbitrary. Okay, so if I'm looking at a social network graph between two people, and if I'm building this on Twitter, okay, how would I determine if there's an edge between 2 people in the Twitter graph? Okay, how do you think I should determine an edge if in the social network graph for Twitter? Yep.
Twitter's probably gonna be a huge.
Well, they do something like this. They keep a sparse representation, okay, but they have really big servers, right? They store all of your tweets after all, right? So they can store the adjacency matrix. It's pretty sparse. Okay, there are some nodes like Selena Gomez or someone probably has a huge number of followers and so forth, but most people don't have that. So, but how would I define an edge? Yeah. Yeah. So if you follow someone, Eij is in E if I follows J, or J maybe follows I, right? So it could go either way. It's undirected. So either following direction, I follows J or J follows I. Okay, but what if I interact with someone on Twitter? I reply to their tweets, but I don't follow them. I found their tweets because they replied to someone I follow, and I saw it, and then I replied, and we have lots of messages back and forth. Or I quote tweeted someone else. Should I put an edge between myself and this other person? So maybe I'm still interacting with them in some way, right? There are lots of ways you can interact with people, and how you design the edges is, okay, if they follow, that's pretty easy way, but there are lots of other ways you can measure interaction. On Facebook is even more complicated, right? The interactions between the users is even more complicated, yeah.
So could we almost say that to them based off the connection between two nodes?
Sure, yeah. So instead, for an affinity matrix, so the idea is Aij will be, instead of 0 or 1, it'll be something in the range of 0 or 1. Okay, I'm going to have some value where 1 means they're really connected. This is very so connected. And this is not so connected, but it might make sense to have a 0.5 or a 0.7 or a 0.1, right? If I have some basic interaction with them, right? So what do we know that fits this pattern, where a 0 means small interaction and a 1 means large interaction? They're somehow related, closer to each other. Well, one way of thinking about this is by setting Aij equal to the similarity between some object xi and xj. So if I have some defined notion of similarity, like Jacquard similarity, or like the cosine similarity between things, I can define an adjacency matrix in this way by describing the pairwise similarity between all the objects. We can talk about like a kernel, like a Gaussian kernel, the kernel distance, maximum mean discrepancy I talked about. That can define a similarity between objects, between 0 and 1, and I can build my affinity matrix in this way. And then I can still build my normalized Laplacian matrix as D minus A, where Dii is going to be equal to the sum of j equals 1 to n of Aij. So this is kind of the degree of node I is the sum of the affinities. Okay, and then I can define the degree of an affinity matrix, and I can define the unnormalized Laplacian as before. So if I have a similarity function between objects, and I want to do spectral clustering or top-down clustering, this is generally the way to do it. I plug in the similarity, I compute the affinity matrix, I compute the degree matrix of the affinities, and then I compute the Laplacian, I do the eigen decomposition, and I can do a top-down split. And this gives me a way to do the top-down split for spectral clustering. Okay, so this is a kind of a more general approach than just for graphs. Anytime I have a similarity, if I have a distance, I might want to convert it to a similarity through one of the ways, 1 minus a distance or this inner product kind of decomposition. Okay. So this was the last thing I want to explain is the Laplacian matrix instead of the normalized Laplacian. Okay, so the Laplacian matrix is a variant of it's kind of a replacement in the mechanisms I talked before for the place of the unnormalized Laplacian. So be the normalized Laplacian or just the Laplacian matrix, and it involves one more ingredient in order to construct this. So it's a little bit weird if you haven't seen this before, but I'm going to take a matrix to a power. Okay, and taking a matrix to a power can be a little weird. If it's a square matrix and the power is 2, I'm multiplying them together. but I want to take a matrix D to a negative fractional power. What does that mean? Well, this is easy to define if it's going to be a diagonal matrix. If it's a diagonal matrix, what I want to do is I can take the entries on the diagonal and I can take those each to that power. In this case, it's a negative 1/2. So this used to be a 0.577 used to be a 3, right? So the degree of A was 3, and negative 3 to the negative 1/2 is 0.577. Okay, 2 to the negative 1/2 is 0.707. That's 1 over square root 2. So this is equal to 1 over square root 3. This is 1 over square root 2. This is 1 over square root of 1. Okay, so this is the D, the diagonal matrix D to the negative 1/2. And so in matrices, I want to normalize. When you normalize something, you divide by a scale. I can't divide by a matrix, but I can take it to a negative power and then multiply it. Okay, and so basically, to the Laplacian, I have a negative 1/2 because I don't know what side to divide it on. So I divide it on both sides, but only half of it on both sides. Because it's a square matrix, this kind of all makes sense, like the right thing to do. And what it's doing is it's kind of normalizing out the degree of each vertex. So what's happening is now I see the ones on the diagonal instead of the degree on the diagonal. So I'm reducing kind of the importance of nodes with very high degrees, because that doesn't matter itself so much in my clustering. The degree being high, I want to know how it's connected to other things, not is its degree by itself high. Okay, and so there's kind of, it's the Laplacian is the identity matrix, which is all ones with zeros everywhere else, minus this normalized, which is D to the minus 1/2, multiplied on both sides by the adjacency matrix. Turns out this is equivalent to D to the negative 1/2 times L0 times D to the minus 1/2, right? So I can decompose L0 into the degree minus the adjacency, and the D to the minus 1/2 on that first term turns into the identity, and then I get the adjacency matrix gets squashed in this way. Okay, so I've taken the original unnormalized Laplacian and normalized it by the degree, and I get this thing. Okay, so now if I apply the same sort of technique before, I can look at the eigenvectors of this Laplacian matrix. This turns out to kind of be useful for the normalized, for optimizing the normalized cut. And now I want to take kind of these values and put these on this one-dimensional line. Okay, and then use the split on these values instead. That's mostly what I want to do. I actually want to do something like this. I've drawn it now in 2 dimensions. So you kind of see the first two, V2 and V3 at once. I've done 2 things here. I've not just drawn them with their values on the eigenvalues. I've multiplied. This is actually what you want to do is this value is V2 times 1 over lambda 2. So I've taken the importance, which is the lambda, and I've 1 over the importance, and it turns out you want to take the, is it 1 over this? I think it's just 1 over lambda 2. One over lambda 2. So V2 times 1 over lambda 2. So I've taken a value which is 0.38 for A, and then I've stretched it out by basically multiplying by 8, right? So 0.38 times 8 is about, what, like 4 or something, and then that's about where it is on the x-axis here. Okay, it looks pretty similar than before. You've noticed the ABCD is over on the positive side instead of the negative sign. The eigenvalues are not unique up to a sign. So I can change the sign, and that depends on some initial randomness in my implementation or something else. So the sign doesn't matter on the eigenvectors, okay? And these are even more spread out. So once I've used this lambda 2, I've spread them out even better here. And I've forced them to be these two clusters. That first cut should be even more obvious here, right? This first cut into S here is even more obvious once I've drawn them in this way. Okay, so the graph is input. This was a picture. It happened to be grouped this way. I didn't know how to draw it. That's a convenient way, but this says I really want to stretch them out. I still can't distinguish between A and D here. Okay, and the other difference you notice is that H is kind of pulled back in a little bit. And if I did that four-way split, F and H would be grouped together, right? So it kind of says I'm better off not splitting H off by itself because I'm dividing by everything else on the same side. So that normalization might have forced me to group F and H together instead of keeping F, G, and E together. So that might be better what minimizes the normalized cut. Okay, so if you're actually doing spectral clustering, you want to kind of use the normalized Laplacian, which is this one extra step where you use this d to the negative square root, which really isn't so bad. And then you could use a graph, or you can use any sort of affinity matrix to describe the similarity between objects. You put it in this method and you do this top-down split, and you stop when you're satisfied, right? Again, the common way to check the number of clusters is you kind of plot some score of how good the clustering is as you're increasing the number of clusters. And when you get to some elbow point, then where it seems to kind of be leveling out, then that's where you would stop. Yeah.
For multiple clusters, like they all
so yeah, so usually the first eigenvector will help you find kind of one split into two clusters. If there were like really three very clear clusters in the graph, what you might find is that the second eigenvector, the third one, V3, might help you determine where the split between, say, if there's clusters S1, S2, and S3, S1 might get split off by the first eigenvector, and S2 and S3 might get split off by the second, right? So each one is kind of giving you some mode of variation in the data.
So if the eigenvectors are like the first three relatives, would that be kind of
yeah, right. Yeah. So if again I look at the eigenvalues here, and I want to know really how many splits are there, well, when I see a big jump, that might tell me. And right here, it's pretty clear, splitting between C and E, that first top line cluster, really makes sense. And then the rest of them kind of levels off. So I could use this as my plot to decide where to cut things and just make one cut here. This would be a reasonable use of the elbow method. Yeah. Although sometimes you could get a graph, if you get a graph that looks like right? So a bunch of clusters like this that are very sparsely connected. This, you might be able to describe this with two eigenvectors, and you could see I can draw it pretty well, so the eigenvectors could. And so then I could see these both splitting on the first and the second level of either plotting them at once or recursively splitting again. So I can either try and plot the first two eigenvectors and then look for good splits there, sometimes with k-means clustering on top of that, or I could do the first eigenvector, which might give me this split, And then on the second eigenvector, well, I would do it recursively on just this subgraph, and then I would find this split. And I would also do it on this subgraph and find this split. Right? So which one is the right version of spectral clustering? I've seen, it depends on how allergic you are to doing a lot of eigendecompositions. If you only want to do it once, you do it once and you embed it where these start getting big, and then you maybe run k-means on top of that. Or if you're willing to do it recursively, then you do it a few times, and you split it a few number of times. Both of those are valid ways of doing it. So great, so we'll stop here and we'll talk about streaming algorithms and frequency approximation on Wednesday.